In this video, we are going to discuss on the topic of RF passive components. So the first passive component that we are going to discuss is the transmission lines. So in this video, we'll be discussing about why do we need the transmission line theory and how does actually the transmission wave concept work and its behavior in case of low and high frequencies and how we can represent it in terms of the lumped and distributed models and how does the transmission line parameters actually work. Okay, so the first topic that we are going to discuss is the need for the transmission line theory. So just assume that you are going to connect a wire between a two component. Basically, it can be any circuit, a battery. Then I'm going to connect a wire. Then I'm going to connect a bulb to the other end. Okay. So, do you think actually the wire will affect the performance of the circuit? Sometimes, if we are dealing with a low frequency, we could say that the wire actually does not cause any effect in case of the conducting properties or the movement of the electron from one place to another and the working of the bulb. But when I'm dealing with the higher frequencies, obviously the wire will have a huge effect in the transmission of the signals. So transmission line theory will actually help us like how the voltage and current is traveling through the wire when we are treating it in the higher frequencies. Okay, actually what is the assumption that we have in the circuit theory is that when I'm going to connect a very long wire between any two components in case of an electrical circuit, the wire is considered to be a perfect conductor when we are dealing with the circuit theory concept, but actually the answer is no. When I'm going to connect the wire between two different components, it itself will provide a resistance, inductance, and capacitance to the circuit. But when we are dealing with the theoretical concepts of circuit theory, we assume that the wire will have zero resistance and there is no delay which is caused by the wire, and the voltage will be same at every point on the wire, and the current reaches every point instantly within the time period when it is switched on. But in reality the answer is no. Okay, so when I'm going to connect a bulb along with the battery and a wire, there will be same voltage. If there is same voltage throughout the wire, I can apply the Kirchhoff's voltage law. But if there is no no similarity between the voltages at different points of the wire, the Kirchhoff's voltage law will become, the Kirchhoff's voltage or the current law will become invalid, right? If in case the Kirchhoff's voltage law is valid, we could say those circuits as a lumped circuit model. Okay, actually what happens at higher frequency is, now let us assume that I'm going to connect a 10 gigahertz RF generator to an antenna via the wire. So what happens here is that the signal is going to change billion times for every fraction of second. So the signal does not appear throughout the wave. In order to understand that, we can just simply assume you're going to throw a stone into the pond which has water. Okay, so what actually happens is the disturbance which is happened by the stone is actually not traveled to every point of the water at the same time, but it takes some time for it to travel from one point to another. So that disturbance is here equated to the flow of voltage and current in case of the transmission line. Okay, so as if the disturbance in the water, the voltage or the current in the transmission line also flows through the transmission line in the form of waves at higher frequencies. Okay, so we could also discuss it more in detail in the traveling wave concept. The voltage signal moves through the transmission line actually in the form of wave. Okay, as time increases, like initially the voltage will appear only at the starting point of the wire, right? Then it moves from one place to another. For example, let me assume that when the time t that is equal to 0, it appears only at the end point of the wire. When the time is 10 second, it moves from one place to another, and when the time is 20 second, it moves from one place to another, and when the time is 30 second, it moves from one place to another, right? So from this we can easily say that the voltage at any point of the wire actually depends upon two different parameters only. One is going to be your time, which is going to define what will be the voltage, and the second one is the distance, which will also define what will be the voltage in the wire. So when I define it mathematically, we could say that v z of t, that is equal to v naught sine omega t minus beta z, where the t and z is nothing but the time and the distance of the wire. Okay, so in case of the traveling waves, the voltage will not be same at every point of the wire. Okay, as I have explained it earlier, at initial instant of time there will be a different voltage. If I calculate the voltage at a point a, it will be a different one. Here I have defined it as plus 5 volt. At point b it will be around plus 2 volt, and point c it will be around minus 3 volt. We could easily define that at different points there is actually a different voltage which is flowing through the wire, and this is why the distance and time plays a vital role in defining how the circuit is going to behave. Okay, unlike DC circuits where the voltage will be same all over the wire, in this case it will not be actually same. Okay, so now we can define what is actually the influence of the low and high frequencies. Let us assume that I am going to deal with actually a very low frequency of around 1 megahertz. So the wavelength will be 94.86 meters, and if I assume the length of the wire is about 1.5 centimeter, we could easily define that the wavelength is actually larger than the physical length of the wire. In that case, wavelength is nothing but the amount of distance the wave actually covers in 1 second, right? So within 1 second, the wave can actually travel 94.86 meters, and the length of the wire is very much smaller when compared to the wavelength. In that case, the voltage will remain the same at any point on the wire. But if I talk about higher frequency, so here I am assuming the higher frequency as 10 gigahertz, then the wavelength will be around 0.949 centimeter. Again, if I am going to consider the physical length of the wire as 1.5 centimeter, here the wavelength is smaller than the actual physical size of the wire. In this case, the voltage at different points appears to be at different values. Okay, so in this case I'll not be able to apply the Kirchhoff's laws, will be unable to calculate. Okay, so in case of Kirchhoff's law, we assume that voltage will be constant throughout the wire and current is same everywhere. But in case of higher frequencies, voltage actually varies instantly and current also varies continuously. That is why we will not be able to define the Kirchhoff's law for the circuit with high frequencies. So the solution for distributed model is that instead of treating the wire as a single conductor, what we could actually do is we can split the wire into different small components. So these small sections, the voltage will be constant and current will be constant. In that case, we'll be able to apply the Kirchhoff's law for those small sections, and this forms the basic of the transmission line theory. So when we are talking about the distributed parameters, every small section of the transmission line will contains a four component in it. One is the series resonance, another one is the series inductance, another one is the shunt capacitance, and another one is the shunt conductance. Talking about the series resistance, due to the conductor resistance, there will be actually a power loss, and due to the produced magnetic field, there will be a series inductance, and whenever there exists a circuit which is separated at a specific distance, it will store the electric charge. There we will have the shunt capacitance, and shunt conductance is the leakage current through the dielectric. Okay, so why should we actually use the transmission line theory? Basic is the thumb rule is that we use transmission line theory when the length is greater than lambda naught divided by 10, and if lambda is less than 10, sorry, if L is actually less than lambda divided by 10, the ordinary circuit theory analysis is not applicable. Okay, so while we are talking about the applications, it is actually used in the RF circuits, microwave engineering, antenna design, where the actual circuit theory concepts couldn't be applied. Okay, so that's all about this video. Thank you very much.